Yes, well, thank you for the invitation to speak, Joe. I've been keen to come and see what the Grantham Institute's up to under its new leadership. I thought what I'd try and do in this talk is give you a bit of a flavour of what we do at the Hadley Centre, and then a bit of a look at some of the questions that we're trying to address and how we're addressing them. So this will be a fairly kind of broad level discussion. No equations, I think I'm embarrassed to admit. Yes, is this a first? Anyway. And of course that's late at night one evening in the Hadley Centre and beavering away trying to solve the Earth system problem. So I was aware that not all of you will know what we do at the Hadley Centre. Just got a couple of slides on that, and then I'll talk through a bit of the current programme, sort of looking at the past. So we've got a big observational programme, the present, so the role of greenhouse gases on the probability of events now, so attribution science, and then core business for us, predictions of the future. And then I'll say a little bit about this science for services. So climate services are a big buzzword at the moment. So what's our contribution to that? I'll just say a few words about. So in this environment, I probably almost don't need to put these up, but I'm definitely going to, because I think it begs the question of what climate science is for now. So you'll all be aware that the IPCC report, Working Group 1 2 years ago, reaffirmed the AR4 view that changes in the atmosphere, cryosphere and ocean show unequivocally that the world is warming. So first question of climate science, is the world warming? Second question, if it is warming, is it due to human activities? And I think arguably the IPCC was set up to answer those two questions, right? So the answer to the first question is yes. Observations show unequivocally the world's warming. Then using a combination of models and observations, the IPCC was able to conclude that it's extremely likely, so 95% in their calibrated language, that human influence is responsible for more than half the warming since 1950. So again, this is a very strong statement. It's a consensus view of thousands of independent scientists that the world is warming and it's extremely likely due to human activities. So as I said before, arguably the IPCC was set up to address those two questions, and we now got answers to those two questions. So what is climate science for now? This was my interview speech for my current job, because we don't need to keep doing that if we know the answers. Now, it was quickly pointed out to me when I took the job that just because 2,000 scientists agree that the world is warming does not mean that the world at large agrees with that. So a big part of what we do at the Hadley Centre and indeed at the Grantham Institute is devoted to communication of the present state of climate science and the evidence to underpin these statements here. And in fact, as I'll say in a few minutes, one of the core roles of the Hadley Centre is to provide advice to our sponsoring government departments on these issues. So communication and outreach is clearly still an important aspect of what we do. But then there are really three timescales of looking into the future, particularly, which I think can help organise our thoughts. So the first is on monthly to decadal predictions, so seasonal forecasts going out to, say, up to 5 years ahead. And the users of that are people who are interested in resilience and preparedness. So the kind of cartoon example is, will we get a cold winter this year? And if so, preparations need to be made in the transport sector and so on. Or for agricultural preparedness, should we be preparing for a drought in the coming seasons or years? So that's kind of initialized extended range forecasts really going out to some years. I won't say a huge amount about that, but I'm happy to answer questions. There's then the sort of multi-decadal, so say going out tens of years, projections for wise adaptation. So we know that with the emissions of greenhouse gases that we've had so far in human history, the climate will warm, so we will have to adapt to some degree to climate change. So the question is, how much do we have to adapt to, and what are the regional patterns of those adaptation? And I will say something about how the approach we take to making those. And then finally, the third kind of organising timescale is the much longer timescale, out to 100 years or so. And this really is playing to the mitigation agenda of given emissions and given the amount of carbon dioxide that the Earth system absorbs versus the amount that remains in the atmosphere, can we quantify that and then that informs the carbon budget that we can emit to keep warming below 2 degrees and all that kind of thing. So the stuff that the COP meeting in Paris will be addressing very directly. But I deliberately wanted to organise it like this because you can see that some of the sort of classical bits of climate science, there's a lot more to it than that. And so it's really moving to an area where climate science is trying to be useful. And that's really what climate services means here. I would say climate science is about providing understanding of the climate system and maybe providing evidence to answer these questions. A climate service is taking that information to turn it into advice upon which you or society could make a decision. So at least at our end of the world, that's an important thing. Okay, so how does the Hadley Centre fit into this? So here's a go at, is this a mission statement? Does Grantham Institute have a mission statement? I should see. Okay, good. So we are sponsored largely by government. So our role is most definitely to provide scientific advice to UK government. It has to be robust and traceable and best possible, etc. On climate variability and change, and it's based on world-leading science. So a lot of the quality or the advice that we provide is based on world-leading science. That's how it can be judged good, I suppose. And I think we have another role, which I'll come back to in a few minutes, which is in a term that sounded a bit clunky when we started using it, the national climate capability. So the UK is extremely good at climate science because of Imperial and Reading University and Leeds University and the Met Office and so on. And one of the big funding agencies, the NERC, NERC, did an audit of the sciences that it supports under John Krebs. And I think weather and climate science came out extremely well out of that audit. And there are several reasons for that, but one is we're a close-knit community. We broadly use the same tools, and I'll pick up on that in a minute. The Hadley Centre is part of the Met Office. We have about 175 staff. The approximation is because it changes, not because I don't know. Some are part-time. And about 2/3 of the funding we receive comes from a core contract with DEC and DEFRA. DEC is the Department for Energy and Climate Change. DEFRA's Environment, Food and Rural Affairs. So the two departments in this country that have a core interest in this. So I'm getting towards the end of the kind of program stuff. So I've got this slide and the next one, and then I'll get on to science a little bit more. So this is what we do. And there are really 4 elements to this. So on the left here is the kind of infrastructure that we develop. So we develop climate quality data sets for monitoring of climate. So there is still a need to understand what the climate's actually doing, particularly on short timescales and at high regional detail. And really our core expertise there is not necessarily in collecting the numbers, it's the post-processing to turn it into climate quality data sets. We then develop a weather forecast model in partnership with the other bits of the Met Office. So that's our kind of core climate model. It's the atmosphere, ocean, ice, land bit of the model. So that's kind of the physical part of the climate system. We then have a team joint with the UK NERC community to turn that into an Earth system model. So that includes the land and ocean-based carbon cycles, glaciers, atmospheric chemistry, aerosols, etc. So that will be our core model to contribute to CMIP6, for those of you who know about that. And then we hold computing infrastructure to actually run the models. So this is big science, and this is our kind of contribution to the national scene on that. And as I said before, I think one of the reasons the UK is good at what we do is we tend all to use this set of models. So it's a kind of a community effort. We then do science with that, and that's what the rest of my talk is going to be about. So there's something on kind of global aspects of climate, so the old chestnuts of the climate sensitivity. Are there thresholds in the climate system, like a shutdown in the MOC and the impacts of that? There's things related to Earth system processes and how they play into the carbon budget. Something I'll talk a fair bit about is understanding how atmosphere and ocean dynamics plays into the interest in climate now. So this is a new focus for us. regional climate and climate extremes, I'll say something about that, and then the delivery of projections, which I talked about. And then maybe if I can just pick out this, I think this going from I was 20 years at University of Reading nearly, and what we did not do was this bit. So this is what distinguishes us at the Hadley Centre from the university department. We have a team of people whose job is to take the scientific output from this and tailor it to what DEC and DEFRA, our government sponsors, need. So in the run-up to the COP negotiations in Paris, what is it? What are the facts and figures that are needed at the fingertips of the negotiators, or what latest piece of evidence about sea level rise can we bring to encourage the small island nation states, or whatever it might be. So we have a team of people that we call the KI, the Knowledge Integration Team, who do this. And it's been kind of an interesting lesson to me that in order to get your science out there, we all want to do that, but actually keeping it really targeted and focused on a few customers is really important, I now realize, because you absolutely need to be able to speak their language, have daily contact with them, and be able to iterate what you supply to them. So we have a very small focus on just a small handful of government departments. And then the climate services bit, which I think I'm going to talk about in just a couple of minutes. So this is, if you like, our contribution to this national climate capability. And we had a go at mapping that. And my challenge for you is to see where Imperial and the Grantham Institute should come on this. So the point of this, Professor Haig, before you're rude about it, the point of this is to show that it's a deck of cards. So if you took out one of these elements, then, for example, here's the National Oceanography Centre. They supply the physical ocean model that's part of our climate model. So if you broke one of these links, you wouldn't have a basic climate model. Here's the National Centre for Earth Observation. Without that, some of the evaluation that Helen and I were just talking about simply wouldn't happen. So it's kind of a useful way of encouraging funders to see the whole piece, and I think encouraging us as a community to see that we have different roles and responsibilities. And I wanted to show this here because this is very much focused on the physical end of the climate system. And we touched on at lunchtime that there's also a great need for to understand better the impacts of climate change. So the UK has a climate change risk assessment which is updated every 5 years, and there is no equivalent community of people who deliver scientific knowledge that underpins the climate change risk assessment. It's a bit of a random free-for-all, actually. So my view is that there's some thinking we could do to take this into other areas. To give you a flavour of the kind of climate services we're supplying to DEC and DEFRA at the moment, there are others, but these are the core ones. These are the things that are really driving the science that we're doing underneath. So on DEC side, DEC is the Department for Energy and Climate Change. So you'll remember under the previous government, the Green Deal, which was encouraging people to insulate their homes. Until recently, there were various subsidies to encourage renewable energy. Fracking is an interest. So what can climate science offer to this kind of debate? Well, we can think about the amount of renewable resource which is available and how that might change in the future. We can think about how the relationship between wind resource of energy versus demand. So often you get high demand in periods of cold winters, which also happen to be periods of low wind. So wind is not such a good bet then. So there's quite a lot we as a community can offer that kind of thing. Carbon budgets and mitigation. So for the negotiations in COP, this is absolutely core business. So for DEC, we do a lot of work with them around that. And then generally, DEC are interested in knowing what is the latest climate science because it gives the UK a strong position at the negotiating table to come with a deep and credible understanding of what we know and what we don't know. On the DEFRA side, there's obviously a huge interest in the agricultural economy in the UK. But actually, again, it came up at lunchtime. We've got some really fascinating work thinking about supply chains. So if we're thinking about the impacts of climate change, the impact on the UK doesn't have to be in the UK. If there's a storm or if there's a drought in Texas, that leads to inflated wheat prices, which has an effect on our economy. So we're exploring some of those impacts here. And then DEFRA runs the climate change risk assessment, so it's the department in charge of the UK's response and adaptation to climate change. Okay, enough. So that's the draw, and I think the lesson I take from all these new drivers is that what we need now is the global mean temperature is a useful metric to try and galvanise action, but it's not the measure of change we need to inform these services. What we actually want is information about events of some sort, and I'll talk a little about what I mean there. So in fact, this is one of my main messages. I feel the climate community has been very lazy in its use of the term extreme events, and this is my pitch to offer two perspectives on that. So the first thing I would identify as a climate event, so this is something like regional extent and seasonal in duration. So for Europe, we have a pretty clear message on what climate change will do. It will bring hotter and drier summers and warmer and wetter winters. So those are climate events, right, because they're over the whole of Europe. However, this is also the conventional climate change message, because this is for changes when averaged over 30 years. Well, actually, most of the users that we speak to want to know whether actual summers are going to be hotter or drier, and the general public, and the Daily Mail in particular, will throw rocks at us when it's not a warmer and wetter winter, but when it's a cold, dry winter. So understanding the shift from our present climatology and balance of rainy, miserable summers versus the hot summers, and how that balance will change into the future is the kind of challenge I think we've got here. And stop talking about 30-year means and start talking about frequency of events, if you like. So what can we say about these seasonal climate events into the future? So I've got a couple of illustrations of this to sort of give you an idea of the kind of thing that we've got in mind here. So the summer 2003, they're both European examples, but I could have chosen many from other parts of the world. Summer 2003, of course, is an iconic climate event for Europe. So this is the famous picture from Christophe Charles' paper in Nature showing the surface temperature anomaly through June, July and August. And the scale goes from -10 to +10 on the colour bars here. So +10, and it's typically +7 or so in this region, 7 degrees above, the mean temperature was 7 degrees above the climatological average. So the UK is not so much warmer on that scale, but this is the UK scale from our climate monitoring data set. And this is mean maximum temperatures for June, July and August. And the dark red here means greater than 2 degrees above that. So you can see that the southeast, and in fact large parts of Scotland, were more than 2 degrees in maximum temperature above average. So this is already the kind of stuff you might be interested in for a climate service. So at that point, I was working at Reading in 2003, but I was doing 1 day a week working at Arups, who were consulting engineers who advise on the built environment. So the kind of question that was being considered then was, in a changing climate, how feasible is it going to be to keep buildings cool in a warming climate, or will we all need refrigeration units? And so 2003 we could use as a kind of proxy for events of the future. So then you want to know how many of those events you're going to get in the future. So there's a time series which I won't go on to. So 2003, Peter Stott and others did a so-called attribution study on this event. So an attribution study, we run a climate model with measured emissions of greenhouse gases and then with pre-industrial levels of greenhouse gases. And in the different model runs, you count up the number of events that give temperatures like this over Europe with pre-industrial greenhouse gases and with measured greenhouse gases. And by looking at the difference, you can assess how the greenhouse gas emissions have changed the odds. I'm wearing out the bulb on this thing. How they've changed the odds of an event like that. So Peter and his colleagues were able to conclude that the odds of temperatures that we saw in 2003 were doubled because of emissions of greenhouse gases. So we thought it would be fun to go back since then, because that's more than 10 years ago. So we've got 10 years of data since then, and that's what's being shown on this plot. So the inset here is showing the area over which we've taken Europe, so UK, Scandinavia, and the Mediterranean. And the colours here are showing you the colours of the warm anomaly associated with the 2003. And the time series here is showing you that temperature just for the summers, June, July, and August, but for each year going from 1900 to present day, and then projections going into the future. So what you can see over the 20th century is that those numbers bounce around. There's a bit of a dip post-war, just like in the global mean temperature, a rising in the late 20th century, and then 2003 sticks out here as more than 2 degrees above average. The blue here represent model simulations, but with pre-industrial levels of greenhouse gas emissions. So the natural variability gives a span of about plus or minus between 0.5 and 1 degree. So you can see that summer 2003 is firmly outside of the natural variability a model would predict for pre-industrial greenhouse gases. So there is a signal of greenhouse gas on this. The orange that you can just about see under there going into the red are simulations with the measured emissions of greenhouse gases. And then you can see that the 2003 is within the range, although it is very much on the upper level. The red are projections with a business as usual, so a high emissions scenario. So you can see warming for the European region in summers, warming by, say, between 5 and 10 degrees going out to end of century. But what you can also see is that the measurements during this time have continued to warm. I also think this is a really nice picture because this is a period during which the global mean temperature has famously not warmed very much. So firstly, it's showing the multi-dimensional nature of the climate issue. Just because global temperatures don't go up doesn't mean to say regional temperatures do, and in fact they have gone up during this period. They continue to rise at a rate which is consistent with the business as usual, so a rapid emissions scenario. So actually, if you're living in Europe and summers are an issue for you, this is telling you that we're still on a pretty bad trajectory, actually. One of the conclusions from Peter Stott et al.'s work in 2004 is that heat waves or events like the 2003 event here would be the norm by the 2040s, and that's just based on extrapolating that line here, 2 degrees above, sits in mid-range by about the 2040s. And what we can see is that we remain on that trajectory now. So I think it's a really nice way of drawing together an event that people experience, particularly impacts people, the context of how greenhouse gas emissions played into that, and then an update on the future of our trajectory since then. So there's an example of how we can piece together a story on an event and then project into the future to sort of pull this package together. Here's a kind of contrasting example, my second and final example of this, and this is again a UK, and it's the summer of 2012. I've been using this for a while now. In most talks this has been, oh yeah, we remember that. It was my first summer in Devon, actually, and Brian, you'll remember that the spring after this, we organised what the media described as an emergency summit, because even the Met Office were baffled by these. It was a very odd thing. We decided we wanted to understand these events and the role of natural variability versus greenhouse gases. So we organised a science meeting, and people like David Shupman from the BBC said, "Why are you barring the press from this?" Anyway, 2012 was an absolute stinker of a summer. Again, this is our climate monitoring data set. The dark blue here it's showing June rainfall. Dark blue is more than double, above double the average we'd expect for June over the UK. So most of the UK was really wet, apart from bits of northern Scotland. Here's the time series going from 1910 up to present day for the whole of the UK. So UK rainfall does bounce around quite a lot, actually. But you can see that 2012 did stick out. So the message we've all been talking about for climate change in the UK is hot, dry summers. And then you give me 2012. And moreover, 2007 wasn't much better, and there's certainly plenty of that. So, what do we tell people about that, and what's our scientific understanding here? So this is an example where I think we understand that summer rainfall in the UK has a strong driver from natural modes of variability in the physical climate system, which is why I picked this example. So here's that rainfall for the UK for the summer, May to September, so an extended summer, going from 1910 through to present day. And you can see some summers are dry, some are wet. But if you squint, you can see there are periods here, mid-century, so about 1930s through to the late 60s, say. They kind of look like there are more wet summers than dry summers. And then when I was growing up in the 1970s, I was lucky. There were more dry summers, so my summer holidays were all brilliant, than wet summers. And then maybe we're in a wetter phase right now. So there's a pattern of variability known as the Atlantic multi-decadal variability or Atlantic multi-decadal oscillation, where I'm not going to go through all the details here. I think there are experts in the audience who know more than I do. The patterns of sea surface temperatures in the North Atlantic fluctuate. Those, I have to be careful with Sir Brian Hoskins in the room. There's a coupled climate system, and the storm tracks in the North Atlantic respond to the sea surface temperatures, possibly feed back on them. And this shifts the rain-bearing weather systems during the summer so that the preponderance of the weather systems either go north of the UK or hit the UK. So this is that index here. I apologise, it's a little faint, going from 1900 here to present day. And the periods where this index is high here, mid-century, is the time when on average the rainfall is greater. The period when this index is low, which is on average when we've got the drier summers. And at the moment we're in a high phase, although there are hints that that index is shifting down. And in fact our decadal predictions out to 5 years do indicate, you heard it here first, that the sea surface temperatures are slipping down there, which might indicate that we're seeing an end to these wetter than average summers. Have to be very careful what you say. One of the biggest differences I found moved from a university to the Met Office is that everything you say when you speak with the Met Office badge is interpreted as a forecast. So in a university, you guys are paid to be wacky and off the wall. I'm paid to be very cautious now. So summer 2012 was almost certainly part of this multi-decadal oscillation of wet summers and drier than average summers. And I think the climate science community are beginning to pay a bit more attention to this. So on the one hand, we've got the climate change signal, the warming signal, as exemplified by this temperature change plot. And on the other hand, you've got the side of the community that I come more from, where we think about the atmosphere and the ocean as turbulent fluids, which do their thing with weather systems and so on. There's an implicit assumption, I would say, that these two elements of the climate system are independent, because quite a bit of the radiative balance work that leads to understanding pictures like that take the atmosphere to be a column that's in radiative convective equilibrium. Whereas this is all about north and southward heat transports. So I think that the challenge for climate science now is to build these two strands of our world together to understand things like these multi-decadal oscillations in the context of a greenhouse gas warming. So here's a slightly crude example. I almost pulled this out, so I'll be interested in what you guys make of this. So at a very crude level, the amount of precipitation that accumulates in the UK over a winter or a summer, this is winter now, is something like the number of storms we get multiplied by the amount of rainfall in the storms, right? The point is that a mantra of climate science, which has to be right from basic physics, is that as the world warms, by Clausius Craperon, the atmosphere can hold more moisture, so when it rains, more can rain out. So that would potentially change that factor in this crude equation. But then the amount of rainfall we get is there's this factor, the number of storms. So the number of storms, I guess, in my simple world now is where the atmospheric and ocean dynamics come in, so things like the Atlantic multi-decadal oscillation. But then maybe we see a climate change signal in the rainfall because of the Clausius-Clapeyron. Then there's the residual question of whether the climate change signal is affecting the modes of variability. In any event, to have a first look at this, we assumed that the number of storms was not affected by the greenhouse gas signal. And this is a test to try and test that hypothesis. So here's winter rainfall in the UK, 1900 to present day, and it bounces around a lot. So you'd have to be a brave person who said there was a trend in that over the 20th century. So I'm certainly not going to argue that. So what we did was we did one of these sector analyses. So we took each day in each of the winters and identified the weather type. So whether it's a blocking thing or a southwesterly mobile situation, and one can split each day into a weather type like that and then correlate the amount of rainfall you get on the different weather types to effectively subtract out the part of this which is due to the different number of storms each year. Okay? So what we've tried to do, using pretty crude statistical correlations, is to try and factor out the number of storms from the accumulation of winter rainfall in the UK. And this is what we end up with. So it's still a noisy signal, but it's not as noisy as that. And there is a trend here. I'm not going to state either my or the Hadley Centre's reputation on this, but it's kind of interesting that the rise in rainfall is about 10% over 2 years, over 100 years. And over that period, the UK has seen about 1 degree of warming, and that does fit order of magnitude, actually, with Clausius-Clapeyron. So it's kind of a first look on what you might want to do. I think it's two things. Firstly, it's trying to get the dynamics and the climate change being thought about together. That's a major goal for me. The second is everyone would like now to know about the role of climate change on rainfall, and this is an illustration that the dynamics and the physics are tightly interwoven, and if we are going to unravel those and make sense of them, we need to be careful, even in the observations, let alone the models. Okay, I'm aiming to speak until 10 to 5. Good, okay. Tomorrow afternoon? No, today. So we've pursued a strategy of trying to build a global model that will give us the fidelity we need to address these questions. I won't say too much about this, I don't think, in view of the time. We're aiming to run at a resolution which represents mid-latitude weather systems because they're an important part of the heat and the water cycle, an important part of the rain-bearing things. And we're trying to run an ocean resolution which has a Gulf Stream that separates and has some variability. And there's some evidence that the water cycle is looking a bit more converged at the resolution we're running at. I also wanted to point out, knowing that Arno and others would be here, that we also deliberately run much higher resolutions of the versions of the models than we can afford for the projections to see what's reliable and what might not be reliable. And I think one of the really interesting things we've been doing, that I've been pushing, is to run ocean. So our standard resolution for the ocean is 1/4 of a degree. So this is surface currents, I think, going from 1 degree, where the ocean eddies are all parameterized by the famous Gent-McWilliams parameterization. 1/4 of a degree, where eddies are permitted. It's not the kind of invite you want to a party. You're permitted to invite, but you're not embraced. And this is an eddy embracing or resolving version at 1/12 of a degree. So it's showing you that this becomes much more eddy-rich by this resolution, and we've got some eddies in our standard run. So we've run some short coupled simulations at this resolution, and what we're seeing is better fluxes associated with the ocean eddies, but actually also, even more interesting that, the bathymetry, so the ocean topography, is much better resolved. And this is doing a much better job, particularly in the North Atlantic, of the cold overflows. So people immediately think it's because we're resolving the eddies. Well, actually, we've got a much better, for the experts, overturning circulation in the Atlantic, and its variability is much better. We're pretty sure, actually, it's because the bathymetry is giving us better overflows and feed of dense water in the North Atlantic. So it may well be that we can fool this lower resolution model to get that right. And sorry, I'm now going off on tangents. There's a famous error in climate models in the Southern Ocean, so this region here, they generally have sea surface temperatures which are 4 degrees or so too warm. And if you think about 4 degrees in water that's 100 meters deep, that's a lot of heat. So this is a big problem, and there was a school of thought that resolving the eddies would fix it, and it doesn't. It helps a bit, but it's not the answer. So one of my areas is in the ocean mix layer, which I'm not going to talk about, where we also think there may be some improved skill in the Southern Ocean. Okay, so I'll get back to my theme here, which is about the climate extremes. And I'll just give you a first view. So the question I posed was, okay, we're saying the main message is hot, dry summers, warm, wet winters. Well, how will the frequency of the other types of seasons, the cold, dry winters and the wet, miserable summers, change in Europe? And this is a first look at that. So in the top panels, we're looking at temperature, in the bottom panels, precipitation. So here, this is the probability of cold winters, in effect, in England and Wales. And you can see they start, because of the definition, they start at about 40%. And they do drop off. But by the 2040s, 1 in 10 of what we would currently regard as a cold winter, we're still seeing 1 in 10 of that temperature. So this gives us a look on the change in frequency of those. I think the interesting one is the summer precipitation. And again, I'm not sure the numbers on this I would stake our collective reputations on, but it's an interesting view. So this is effectively the probability of wet summers. So this is the natural variability signal. And again, because the definition, they're coming out at 1 in 3, 1 in 5 or so. But that's much flatter. So this is saying that according to this modelling system, that mode of variability is not going to be affected by greenhouse gases. And the variance in summer rainfall in the UK is probably largely determined by those kind of effects and isn't going to change too much in the future. So I think irrespective of the precise numbers here, there's kind of an easy take-home message, which is it seems to me that the old message of warm, wet winters, hot, dry summers, is implying that we're just going to live in a world where you just have to crank everything up a bit, and it's not going to be like that. It's going to be an expanded range of climate that we're going to have to experience. And in rich countries like the West, we will have to do things to cope with that, but we can afford it. But other nations that don't have that wealth are going to have to adapt to this wider envelope, and it's going to be tough for them. Okay, so those are the climate events. So I've now just got a couple of slides on the end on, often it's the weather within these seasons that we're interested in. So the aim of this strand of work, and this is our regional modelling work now, is to understand the character of high impact weather in a changing climate. That's the kind of goal. So when we get convective rainfall systems in the summer, will they increase by Clausius-Clapeyron, or are there other factors that might change that? And similarly with wind events. So the tool we're using for that is the tool that's used for the UK weather forecasts. And the innovation here is that the convection scheme for the experts is switched off. So this is a model where the thunderstorms are resolved partially within the model itself. So we think it does a better job on convective rainfall than a standard model would. So these are some results that Lizzie Kendon led on and got published last year. This is the observed by the radar network heavy rainfall events, and heavy means top 10 percentile, I think, here. In the winter and then in the summer. I always slightly struggle with the spatial pattern. Any experts want a bit of homework? Why are we getting heavy rainfall events? This is 15-year climatology in these regions. I don't see a pattern there. Here I do see a pattern. This is Wales, where there's topography, so this is topographic enhancement. And these are the changes for winter and summer, and on the left, through a model that would parameterize the convection, and on the right, on the new model that represents the convection and the heavy rainfall. And there's some quite comforting news here. So these are changes in the heavy rainfall events. The blue means a change, flipping heck, of the units are millimeters per hour. So if a heavy rainfall event now is about 4 to 5 millimetres per hour, this is saying it will increase by 2100 under high emissions by 1 to 2 millimetres per hour. So 25–30% increase in rainfall. So that's Clausius-Clapeyron pretty much. With the convection permitting model, we get broadly the same pattern actually. There's a little bit of extra enhancement over the topography, particularly in Wales, but I think that's just because the topography is better represented. It's just the bathymetry effect on the atmosphere. We're seeing more detail. So that's kind of comforting because most of the rainfall in the winter comes embedded within synoptic scale systems, which both systems would represent reasonably well. So there's a demonstration of convergence and maybe robustness there. The bottom plot shows the changes in the summer rainfall, and you can see that the conventional modelling gives, frankly, almost no change in summer rainfall. And this is a model that parameterizes the thunderstorms. The convection permitting gives really quite a high increase in rainfall. So here, the rainfall is, this is 5, 6, 7 millimetres per hour for these heavy events in the purple. And the increases are 1 to 2, 2 to 3, 3 to 4 in the purple. So this is 50% extra rainfall. So are these, firstly, that's a surprise because it's such a big enhancement. So the second question is this credible, or what's the mechanism? So what's going on here, we've analysed these in some detail. The rain-bearing events look plausible to people who look at weather events. They're not crazy weather systems that we would never see. There is a Clausius-Clapeyron effect there, but there's also this enhanced circulation. So as you get the enhanced Clausius-Clapeyron, the latent heat release drives a stronger circulation, which drives a more vigorous thunderstorm. So the character or nature of the thunderstorms in this are different to the present day, and that's where the other enhancement comes. So again, I think it's one of those things that the numbers may not be spot on, but there's some nice, interesting things there. Okay, I was going to talk a little bit about projections. I think in view of time, I'll just say a little bit about this for sort of general information. So I've thought about these extremes and how we might want to give information on those in the future. So the Hadley Centre, one of our core products, if you like, are the UK climate projections. So these are the kind of authoritative projections of climate change for the UK. And the system we use to build those is we run a global model. We run an ensemble of those that I'll come back to. Embedded within that, we run a regional model which adds a bit of regional detail for the UK. We make an ensemble of global model simulations, and then we need a way of converting this set of model simulations into probabilities, because some of those simulations are less likely than others. So the question is, how do you weight them? So we weight them by how well they model present-day climate. So the way we do it is we make variants of our model. So we tweak parameters in a systematic way. We do projections of present-day climate. We see how the different versions of the model predict current climate. We assign a weighting to that version of the model and its projection into the future. And in that way, we turn the ensemble of these runs into a probability for present day and a probability going into the future. So it's a combination of model runs, observational constraints, and then going out into the future. So again, this gives us risk-based constraints. So we're currently designing the next set of projections, and we're trying to learn from the lessons last time, which predated me. Cool. There was a lot of debate about the system used to do this. And, well, I could talk a lot about where our plans are going, but I think I'm going to leave that to the questions. I think one kind of challenge I would throw out to the community is many of the EU member states produce climate projections. Pretty much all of them use different methodologies. So we've got really quite a sophisticated system that gives probabilities of different things happening. The Dutch have decided to go for a very simple system where they have some simulations, one for high impact events, one for low impact events. So there's storylines for the future, and you just take your pick. You go with that, and that's all we're going to give you. The Swiss have a system a bit like us. The Germans a slight variant. So we've got different, we're in a European community where we want to harmonise all that we do, of course. And yet our view of the future is incredibly varied. And moreover, if you're interested in water as one of your impacts, as you cross the border from Switzerland to Germany on your chosen river, the river rates will change because they're using different climate projections. So we're working really hard to try and get some traction on the concept of a European set of climate projections. It seems absolutely nuts to me because this is an expensive business as well. You know, this is 10, 15, 20 people for 3, 4, 5 years working full time on this. So one of my ambitions is to initiate an EUCP project. Okay, so what I've tried to do is give you some flavour of what we do in the Hadley Centre and how we fit with you guys in a university and the NERC centres. I've tried to argue that I can think of two very distinct types of extreme events in the climate system. So one are these broader scale, seasonal duration climate events, which we might hope our global models are faithful at representing, at least that should be our goal. And then there's high impact weather events that happen within these seasons, and there you need a very different kind of modelling, and your whole approach to interpreting the results is rather different. How is the character of the events changing rather than, you know, whether you're going to get an event? And so what we're trying to do, I think, is build modelling systems that can give us a view on the changing frequency of these climate events and the changing character of these high-impact weather events. And I believe this, and it sounds like sort of motherhood and apple pie, but I think this really is what we need for climate services, because there we need advice upon which you can actually make a decision. What do I do about my cooling system in my building or my irrigation system for farming? Okay, and on that motherhood and apple pie, I think I will stop. Thank you very much. Looks like the 518 is still in scope, Brian, if you get your skates on. Hang on a minute, you mean you are going now? That is quite outrageous. Yeah, exactly. Didn't like my answer. Sorry, Apostolos, say it again, please.
So I'm wondering if, you know, with the resolution in global warming getting higher and higher, maybe envisioning that in 20, 30 years, many things will be resolved. Is there like, you know, a stance from the Met Office on how to invest in regional modeling versus global?
Yeah, no, I think it's a really good question. I mean, so I think the evidence that global models are reasonable at synoptic weather systems. I mean, they have known errors. You know, the monsoon in our model the Indian monsoon is rubbish, as you know. There's a double ITCZ still, so there are some issues there, the Southern Ocean warm bias. But the statistics of European weather systems is really not bad now. So what's regional modelling for if we're getting the weather systems right? And that's why I deliberately changed the emphasis of the questions with the regional model. So you get two things. You get more regional detail, so orographic effects. I mean, you know, this is an expensive way of getting what you could do in post-processing. It's things like changes in the character of the weather systems, I would say. So to me, there are some sound barriers, if I can use that metaphor, in modelling. So one is proper resolution of ocean eddies. So 12th of a degree will do that reasonably, although Arnaud may want to argue with that. The other obvious one in the atmosphere, now we've got synoptic weather systems, is convection permitting. But that requires, so we've done some experiments with atmosphere only at 10 kilometres. You get away with switching it off, but the weather systems look pretty weird, you know. You get a better MJO, but the weather systems embedded in it are pretty rubbish. So I I don't think resolution is likely to be something one would want to relentlessly follow, actually. I think you'd want to hit those sound barriers. And I'm not sure 10 years we will be running global convective scale models. I don't think the computer's going to work. Okay, so the answer to that is the crisis will be, can we use the machines that are on offer then? Because Moore's law is not working in the way it has been for the next 5 to 10 years. So you're getting more processors, but the compute per processor is going down. And the models that we use in our community do not work on those computers. So that's the barrier, software engineering and better numerical methods. Otherwise, all bets are off, you know. We're stuck with what we've got now.
Met Office Hadley Centre kind of decoupled the 1 degree ocean version from a quarter degree gone all for any committee. I personally feel that it's not yet established that from a climate perspective you actually gain anything by adding anything. Partly because there are always shallow regions which are incredibly important and high latitudes which have much finer and finer resolution.
Yeah, yeah.
From an academic point of view, it'd be nice to have a model that is supported by the Hadley Centre that we can use more efficiently.
Yeah. Yeah, no, that's a good question. So it's always a challenge. The number of model configurations that we maintain multiplies the effort in an alarming way. 175 people sounds like a vast number of people, but my God, they get used up awfully quickly. So the argument for going to the quarter degree, which is expensive, as you will know if you've tried to run it here, is this plot here is one of them. So this is showing, this is longitude rather, on the horizontal. So the Greenwich date line's here. That's 90, so mid-Pacific is here, and the Atlantic is that region. And this is the number of blocking events in winter. And the European Centre Climatology is the blue line, and the pale blue is the quarter of a degree ocean model. So it's from this plot that the mantra that climate models don't produce enough blocks comes from, plots like this. Because you can see it's about 25% too small. So you'll hear Tim Palmer will say this in every talk, climate models don't give enough blocks. If we go to the quarter of a degree ocean model, we see a better sea surface temperature pattern in the North Atlantic, particularly around the Gulf Stream region. That seems to improve the number of blocks. It seems to improve the mean state of the jet in the North Atlantic, which means we get better blocking, because blocking is just a flow reversal. So the red and the yellow curves here are, one is the quarter of a degree ocean with N96 atmosphere, and the other is quarter of a degree ocean with N216 atmosphere, and they're identical. So it's the ocean resolution which is giving us our improved blocking in the North Atlantic. So that's one of the main pieces of evidence that we use to choose this one. You get better teleconnections from ENSO. So there is, it's exhaustively and exhaustingly documented why we did it, but I'm not quite answering your question. And before anyone else says it, just let me say that the sharp-eyed of you will notice, so not all of my colleagues show the entirety of this picture. Some of my colleagues will focus on the left-hand side. The right-hand side in the Pacific, we're still rubbish like every other modelling centre, and that's because the nature of blocks in the Pacific is different, and it comes down to the MJO, this storms that go across the Pacific and stuff like that. So anyway, the bottom line is, however, sorry, this is an extremely long answer to an apparently innocent question. He's not innocent. So for the UK ESM, which will be the CMIP model, there will be a 1 degree ocean model version of that. So the community are supporting a 1 degree ocean model still as well. Okay.
You were saying that we should all move to looking at things in high frequency sorry, I'm looking at things at what the frequency of an event will be rather than, I'm not really sure what we're doing now. What are we doing now?
I don't know, you tell me. I don't know what you're doing.
I mean, a lot of recent papers,
Why is this new?
yeah. Why
You're
is it?
asking that in a polite way.
Yeah.
Because, no, it's a fair question. It's a fair question, and I've had this challenge more than once. It's new because I think the modes of variability have not had anything like the attention they deserve and how that relates to the climate change signal. I need to try and say, I would say most of the dynamical work was done in universities. That's maybe the polite way of saying it. It is done, but do you know of an example of a way that we know that the climate change signal has changed natural modes of variability in the climate system? I'd be really keen to hear of examples of that. I think there are some, but I don't think there are many.
Yeah, no, because I think we've had kind of vague discussions in our group about, we didn't say how has it changed natural variability, but how has noise changed, how has the noise, that's kind of the same.
Yeah, it's the same thing. One person's noise is another person's music, to quote Brian. But so, yeah, and it's in the observational record. It's pretty hard to say, and you saw how we had to tinker with the UK rainfall because it's confounded by the natural variability. The Hadley Centre, there was little effort explicitly put on these aspects. You're right, in the UK community maybe it was broader. I would also argue that I think the models that we're talking about now are more fit for purpose. I didn't talk about teleconnections too much, but we've been analysing the teleconnection patterns, and of course you can use reanalysis on present day, and the teleconnections look tons better out of the tropics now than they did with the model that we were using 5 years ago. So I would say the models are reaching a level of maturity where it's sensible to do this too. But don't be embarrassed about your question, it's a very good one. No? Okay. So the statistics of the NAO has pretty Gaussian statistics, present day, and in projections, that's pretty Gaussian statistics. They are statistically indistinguishable in projections in the model simulations that we've looked at. Now, when Adam talks about the role of the stratosphere and this new modelling system, he's talking about something slightly different, which is the predictability of the NAO next season. Now, that's different from the variability you get when you run a long run. So we're still trying to understand the relationship between the two, actually, because what we also know from Adam's work is that the real world is more predictable than the models are. So the amount of the signal that's predictable in the real world, you can do this in clever ways, is higher than what you get from the model. So what that means for long-term projections, I think, is a really interesting question. But I think that's the reason for the apparent conflict. Yeah.
I've just got I'm outside of it. I'm just wondering why you would expect your model to be okay for right across the world in latitude. Because I look back to that and I can see three zones. One around zero.
Yeah. Yeah.
Basically, the world is...
That's the Atlantic.
Ocean going north-south.
That's right.
Land either side.
Yeah.
Go to the middle part.
Yeah.
You've got the Indian Ocean and Asia. So you've
Yeah.
basically got one of land at the top
Yeah.
and an ocean at the bottom.
Yeah.
Go to the Pacific, you've got the Pacific, the water
Yeah.
on top there. So how could the model take those three things like that to balance on that?
So the models are based on Newton's laws of motion, the laws of thermodynamics. What am I missing? Continuity, conservation of water vapor. So we believe that they'll work on other planets if they are gas-like planets, because Newton's laws of motion, we believe, are transferable. First law of thermodynamics. So it's for those reasons that we think that the model should work right around the planet. There are geographical factors that you've talked about, so the land-sea contrast and the nature of the ocean play an important role. But again, we what's the right word? Hope isn't the right word. Our confident isn't quite the right word. But the reason we do this endeavour is because we think they're governed by the laws of physics, which we can encode in our computational models. Yeah, it's beginning to look like lobbying.
Does anybody else want last question? Because otherwise that will be the last one. Yeah.
Yeah, I was talking about the physics.
Yes.
So you said you have a low resolution ocean version. Is there also going to be a slab ocean? You know, is the tube is the
No. No. No.
No,
No, we won't support that. Well, we won't support that, no. 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 Because it's, you know, you need flux correction and it's not an energy, it's not an honest representation of the energy cycle. So I think that would be too far backwards for us. So the general issue of how many model configurations, so we make choices based on the resource we've got available to look after model configurations, because this is a very specific software engineering task. We look at the set of projections that we're contracted to produce and the requirements of those. So I think for our responsibility, it's pretty clear that 2 model configurations is what we can deal with, and those are fit for purpose. I think the kind of things you're talking about is, I would say, is the reason NCAS exists, and NOC, to provide additional, because it sounds like a national capability issue, additional configurations that the academic community might be interested in. That would be my kind of UK view on that. But we couldn't afford to do it, I'm afraid. Sorry.
Well, thanks for again. I'm sure you can pin down some more questions.
Of course.
Thanks
Yes.
very much.
All right. Pleasure.